Okay, so you've covered that, so this should be basically just a review. So if we see the PowerPoint, and again, everybody has access to the PowerPoints. A frequency table is a grouping of qualitative data into mutually exclusive classes showing the number of observations in each class. So in the graph on the left side, we have car type. Domestic, those are cars that are made in North America, and foreign, those cars made not in North America. And you see a number under the heading of number of cars, 50 and 30. So can someone just tell me what a frequency is? If you're familiar with it, everybody should know what it is then. Anyone? The number of each item. Exactly, Amir. Okay, so just another name for frequency is a count. You're just counting how many of it in one particular group or in another group. Just as simple as that. And as part of the frequencies, we have a class interval, and class intervals are obtained by subtracting the lower limit of a class from the lower limit of the next class. So if you see on the bottom right-hand corner, there's a little chart there, selling price in thousands of dollars. Those are classes, 15 up to 18, 18 up to 21, and so on. And then beside it, you'll see the frequency. So in the first one, 15 up to 18, you have 8 occurrences. In the next one, 18 to 21, you have 23 occurrences. A class frequency are the number of observations in each class, which is in that little box at the bottom right with selling prices. Those frequencies are part of that class. And the total number is 80 for that particular example. And the class midpoint is a point that divides a class into 2 equal parts. This is the average of the upper and lower class limits. And a frequency distribution is a grouping of data into mutually exclusive classes showing the number of observations in each class. So the chart at the bottom, bar graph, you see the bars increase. That just means the number of occurrences in that particular description have increased. And the bar chart is going up in terms of the frequencies. So I'm just going to show a video, and hopefully this will be a little quicker than last time.
Sue runs a bakery and is trying to cut costs, so she needs to know on which days she can afford to have fewer employees working. In order to figure this out, she needs to know how many customers make a purchase each day. A good tool for Sue to use would be a frequency table, which is a table with a list of items and tally marks recording how often these items occur. For example, since Sue needs to know how many customers make purchases on a daily basis, she could set up a free table by days. Now she can keep a tally or a running total of how many customers come in each day and make purchases. After the week, her completed frequency table looks like this. Notice that she also added a frequency column that totals the number of tally marks at the end of each day. This helps her interpret her data quickly.
Okay, sorry. Back to the PowerPoint. So if you looked at that table from the video where it had the week, those are your class intervals. Very simple, very easy. Okay, I'm going to show the second video on frequency distribution. And sorry, I just have to get that set up.
Do you ever get tired of having the same thing for lunch? Have you ever wondered how many days in a month you eat a sandwich for lunch? A frequency distribution table can help you organize this data to find out. A frequency distribution table is a chart that summarizes values and their frequency. It's a useful way to analyze data if you have a list of numbers that represent a frequency of a certain outcome in a sample. The frequency distribution table has two columns. The first column lists all the various outcomes that occur in the data, and the second column lists the frequency of each outcome. Putting this kind of data into a table helps make it simpler to understand and analyze. If a baseball team scored 0 runs in the first inning, 1 run in the second inning, 3 runs in the third inning, 0 runs in the fourth inning, 1 run in the fifth inning, 2 runs in the sixth inning, 0 runs in the seventh inning, 0 runs in the eighth inning, and 1 run in the ninth inning, we could create.
Okay. So no, we're not using the F table. Okay. The F table is basically for analysis of variance, which is a couple of chapters away. All right. No, F does not stand for frequency, John. So is everybody clear about frequencies? Any questions about this? If there's no questions, we'll just go on to the next slide. Okay. All right. In this one, we're talking about pie charts and bar charts. And I assume everybody's seen this previously, use of pie charts and bar charts. Can someone tell me what a pie chart adds up to? All the pie slices, what do they add up to? Exactly, it's 100% or 1 or 100. So that makes it very easy when you're looking at that, and especially when you're presenting some information. Everybody knows it's going to add up to 100%. It will not go over 100, and it will not be less than 100. Okay, so you could have one slice, you could have, theoretically infinity slices. And what the pie chart does is show the proportion or percent that each class represents of the total number of frequencies. So in that particular pie chart on the slide, you have operating expenses, bonuses, commission, education, prizes. So that's pretty clear regarding the use of a pie chart. And remember, you're talking about the frequencies. And in this case, the frequency is the proportion. And remember, if you can remember from your math, a proportion is a fraction. It's a fraction of the whole. A bar chart is a graph in which the classes are reported on the horizontal axis and the class frequencies on the vertical axis. The class frequencies are proportional to the heights of the bars. So let me get to the next video.
There are two more ways of organizing qualitative data.
Okay, sorry about that. I have to switch screens, so that's why it takes me that long.
Data and displaying them, and these are bar graphs and pie charts. Now, a bar graph lists each measured category on the horizontal axis and the number of occurrences for each category on the vertical axis. So let me show you what that looks like. So back to my old example, imagine that you reached into a bag of candy 16 times and pulled out the following colors. Record your results in a bar graph. So just like before, I'm going to organize that into a frequency distribution. And now based on this frequency distribution, I can organize it into a bar graph like this. So you can see that we have 6 reds, 6 greens, and 4 blues.
So just remember, when you look at the chart, you have the category on the x-axis and you have the frequency count on the y-axis, and that's all you're charting, okay?
Notice that this is a bar graph, as in the bars are not touching each other. If they were touching each other, that'd be a histogram, and that'd be something a little bit different. So now a pie chart. A pie chart is a circle divided into sectors, where each sector represents a category of the data that is proportional to the total amount of data collected. So, what's a proportion? Well, a proportion is a part considered in relation to its whole. Like, for example, imagine a pizza with 8 slices. Your friend takes and eats 3 slices. In this case, 3/8 is the proportion of the pizza your friend took. This can also be represented as a decimal, like 3 divided by 8 equals 0.375.
So I just want to remind people that a proportion is a fraction as well as a decimal. Okay, so I assume everybody learned that, so you can go back and forth. They're all the same. Okay, but depending on how you are presenting the information, you have to be correct with what you're doing. But they all are equal to each other. Okay. Okay, just continue with the video.
That number is a proportion. So back to the candy example, here's the same information as before, now shown in a pie chart. You can see that about 37.5% is given to red, 37.5% is given to green, and the other 25% is left over to blue. We still have the same frequencies as we did before, except now it's organized into a pie chart, which is probably the easiest way of displaying the data, the easiest way of looking at it, but it also doesn't tell us very much about what the original numbers were. It's not as descriptive as the bar graph was.
However, I'm just going to mention that when you do a pie chart, and we're talking about, say, presenting a report to, if you're working at a company and presenting a report to them, a pie chart is a lot easier to understand by your audience than a bar chart, okay? Because they can see the percentages, they all know it's out of 100. It makes it a lot easier for them to discuss the information as opposed to a bar chart, which some of them may not be able to read properly. So just remember that when you are doing reports, the pie chart is the easiest one to explain and the easiest one for your audience to understand.
And those are also, 2 more ways of displaying qualitative data. We have the bar graph and the pie chart, and also recognize the proportions that go into the pie chart. There are 2 more ways of organizing qualitative data.
Oh, sorry, that's just a repeat of the going back here. Okay. Relative class frequencies. So a class frequency can be converted to a relative class. Sorry, a relative class frequency to show the fraction, just like a pie chart, of the total number of observations in each class. And a relative frequency captures the relationship between a class total and the total number of observations. So if we go back to the example of where cars are made, there's 50 that are domestic, or not where they're made, and the number sold. So 50 domestic and 30 foreign. We add the two, you get 80. Okay, so what is the relative frequency of the domestic cars that are sold? It's 50, okay, divided by 80, which is 0.625 or 62.5%. And foreign cars is 30 divided by 80, which is 37.5% or 0.375. All right, is that understandable? Everybody get that? Does anybody not understand? Yeah, okay, good. Very good. Okay, let me just, sorry, I'm moving along here. Not as smooth a transition as in class.
Stephen and Renee are a husband and wife couple that just started a local restaurant business. They want to have a signature steak to serve on the weekends. They asked 20 of their friends to taste test 5 different types of steak to see which steak they should serve. 4 people choose steak number 1. 5 people choose steak number 2. 2 people choose steak number 3. 6 people choose steak number 4. And 3 people choose steak number 5. Stephen and Renee can use frequency and relative frequency tables to analyze and visualize their choices. A frequency table is a chart that shows the popularity or mode of a certain type of data. When we look at a frequency, we are looking at the number of times an event occurs within a given scenario. A relative frequency table is a chart that shows the popularity or mode of a certain type of data based on the population sample. When we look at relative frequency, we are looking at the number of times a specific event occurs compared to the total number of events. The data set for the steak tasting is as follows, where each number represents the steak that was chosen as the best. 1, 5, 3, 1, 2, 3, 4, 5, 1, 4, 2, 4, 4, 5, 1, 4, 2, 4, 2, 2. We can use our data to create a frequency table like this. Notice that the first column indicates the type of steak.
Okay, so can someone tell me what the problem was with that data? Anybody? Okay, you're going to do a study. You're going to measure something. You know, how many times do people watch a particular TV program? You ask your friends, is that a problem? Nobody sees a problem with that? Okay, why is it maybe a problem? This has to do with a design of a study. Yeah, it could be somebody doesn't watch TV. A lot of What did you want to say, Olga? Different shows? Okay, that's not part of the design. Okay, so I'm going to do a survey on, what are the popular shows that people watch? Okay, so I call all my friends and I ask them. Let's go back to the previous chapter where we talked a little bit about sampling. Is that a good sample? Is that representative of the population? No. So what does that mean about the design? It's a bias, exactly, Rijo. It is biased. So what you're going to do is you may get a result that says, well, this is what my friends like, but that doesn't mean that is representative of the general population. So you have to be extremely careful when you are designing a survey or you're looking at data. If you're looking at data that's already been observed and analyzed, that's different. But if you're creating your own data and say it's from a survey, you must be extremely careful about who your subjects are and what are you asking them. So can everybody see that if you designed a survey and you asked friends, what do you think about this? Is that truly representative of the general population? No, exactly. That's what I want everybody to understand, that is that if you randomly stood in front of the George Brown building on what is it, King, and you had a survey and you were doing a survey and you just stopped people as they were coming in and said, excuse me, I want to pay you on this and it'll take 5 minutes. You don't know who those people are. There may be a random chance that one of them may be somebody it may be a friend, but when you do it randomly, you don't know who your participants are in the survey, and that makes the survey more viable. It's more valid. So do people understand that? So in the video, that survey was flawed from the beginning. So all I know is these husband and wife, they asked their friends to try a steak, but that doesn't mean they're going to be regular customers at their restaurant. What if somebody comes in and you don't know what they like? So you see, these are little tweaks that you need to look at and need to examine. And that's, part of the statistical perspective that you must have. All right, so getting back to creating a frequency distribution table. Ms. Catherine Ball of Auto Canada wants to develop tables and graphs to show the typical selling price on various dealer lots. The table on the right reports only the price of the 80 vehicles sold last month at Whitner Autoplex. Okay, this is just all the totals, and what's pointed out is what is the lowest and what is the highest, and why do you want to have that? Can someone tell me why you want the lowest and why you want the highest? No one? Okay, that's how you create your class intervals. All right, I don't think you've gotten to it. Yeah, it's sort of like the range. But what it does is you can say, from 15,546 to, let's say, 16,000 is one interval. You can find the median, but here we're talking about creating a frequency distribution table. Okay? When you have a frequency distribution table, you want to have classes. You want to have class intervals, and they have to be based on a mathematical formula, which we looked at the beginning. The highest minus the lowest over the total. Okay? So it's not finding the average. You're finding the class intervals, John. Okay? So review that in the chapter. And I'm going to show the video. Isn't that one? Yeah, we saw that. Okay, sorry. That's right. Sorry, everybody. Boring, isn't it?
Workforce analysis is used in business to measure the inner workings of companies.
Just a note, have people heard of workforce analysis? No? Okay. Have you had any business classes yet, like formal business classes, or not yet? Yes, okay. So they haven't talked about workforce analysis. It's a very common process within very large businesses, you know, maybe over 100, greater than 100 employees. So you want to see how your workforce is doing. Just an aside, just to see how it, if you have taken that up yet.
Often decisions are made based on how much or how little profit a company makes. However, HR data are vital resources in making management decisions and can provide a wider picture of why, how, and when employees do certain things. Data are pieces of information used to analyze something. Two types of data used in workforce analysis are qualitative and quantitative data. Although there are several differences, the most apparent difference is that quantitative data involves numbers. Quantitative data are numbers, and they can be measured to produce quantitative statistics. HR examples of quantitative data are the retention rate, salary, hours of overtime worked, number of professional development hours taken, and age. Many of these numbers are easily collected in workforce analytics software and can be analyzed with statistics. The term statistics refers to a set of mathematical procedures that are used for organizing, summarizing, interpreting, and reporting information. Gathering quantitative data is fairly straightforward if the data are already being collected. One common type of quantitative data that most of us are familiar with is demographic data, which includes age, gender, race, and education. Combined with other data, it can tell us at what age employees are retiring, whether women are advancing as quickly as men, if enough minorities are being recruited, if education is a factor in production. Qualitative data, on the other hand, involves actions and behaviors that are observed, not measured.
Okay, just so you remember, we'll do this frequently. The qualitative data involves frequencies more often. Okay, so actions and behaviors. So you're surveying or you're making observations, and you say, "Oh, what? Larry went to the bathroom 12 times during the day." Okay, we've got to do something about that. Okay, because other people are only going twice a day. So something's the matter. Either something physically wrong with him, or you know, he's skipping work. He's going for a smoke break or whatever he's doing. That's where you make lots of inferences from your observations.
There are no numbers produced.
Well, that is not true. Okay. There are numbers produced because they're frequencies. So the number of occurrences. All right. And if you have any questions about the videos or what's talking about in the videos, just please ask me. All right, so we're going to construct a frequency table. This is an example. First thing you have to do, decide on the number of classes. So the useful recipe to determine the number of classes is the 2 to the k rule, such that 2 to the power of k is greater than n. So going back to the other example, if there are 80 vehicles sold, so n equals 80, everybody agree with that? And if you say try k equals 6, which means we'd use 6 classes, then 2 to the 6 equals 64. That's somewhat less than 80. Hence, 6 is not enough classes. It's not going to cover the majority. If you have k equals 7, then 2 to the 7th equals 128, which is greater than 80. So the recommended number of classes is 7. So you have to know what your sample size is, n, okay? This is one way to determine the classes, and it's mathematical, so it's not subjective. So you really want to use something that's objective. And if you use the 2 to the k rule, you should find enough classes. Now, one problem with this is, what happens if you have less than 10 in a particular, a frequency of less than 10 in one of the classes? Can someone remember what happens then? Nobody? Okay. So say in this case you have 7 classes, right? You don't have enough data for some of the classes. Therefore, the sample within each class, and we're going to use sort of the normal number, the criteria for the number, it can be somewhat subjective, but if you say only have access to, say, 100 people, and what 2 to the k is going to be close enough to 100. So 2 to the 7th is 128, so that theoretically should cover it, although you have 28 empty spaces, which means there may be some classes that will have less than 7 in each of the classes, okay? And usually the rule of thumb when you're doing statistics is having a sample, in this case for each of the classes, of 10, okay? So it's possible you can have less than 10. I'm not going to talk about how you can resolve that right now, but there are ways to resolve it mathematically. So in this case, we're going to have 2 to the 7th. We're going to have 7 classes. We want to determine the class interval, or the width. The formula is I. And I'm looking at that sign. I can't see that sign. It's the highest minus the lowest divided by k, where I is the class interval, and h is the highest observed value, and L is the lowest observed value, and k is the number of classes. So in the case, step 1, no, I don't think it's plus, John, because we're looking for the class interval. So if the example, if we have the highest value of the car sold, it's $35,925 minus the lowest value, which is $15,546, divided by the number of classes is 7, comes out to $2,911. Okay. In this example, when I do this, I like to be more precise. In this example, what they're doing is they're rounding up to a convenient number, such as a multiple of 10 or 100. So in this example, they're using a class width of 3,000. Okay? However, to be more accurate, you would use the actual number that you found. So you set up your individual class limits. They rounded it to make it easier, so you start at 15,000 up to 18,000, 18,000 up to 21. It actually would be $18,001. up to $21,000 and then $21,001. So everybody clear how the class intervals were created here? Any problems with this? Yes, everybody gets this. That's pretty easy. You know, you're taking the highest minus the lowest divided by the class intervals that you figured out from the first step. Okay, so you have the classes. If you look on the right side, you have the classes. Here are the classes over here, this little finger. Tallies is the frequency. So you have the selling price, and then they just converted this marking into the frequency numbers. Okay, and what's really, really important is your total should be the total sample size. Okay, there should be no changes in that. We're not, you know, if you have a 0, it's a 0. Okay, you know, if 79 cars were only sold in one class, it's 79. So just remember that, because you want to keep all the data. You want to keep as much data as possible, because it's going to tell you more and you can infer results from this. So to convert a frequency distribution to a relative frequency distribution, each of the class frequencies is divided by the total number that we saw earlier. So we see on the left side the selling price, the frequency, the relative frequency, and that is the frequency here, 8, divided by the total number, 80, gives you 0.1 or 10%. And if we go down to each of the classes, and this should always add up to 1 or 100%. And what you can say is, oh, okay, you know, I'm going to look at the highest one. So the cars that were between 18,000 and 21,000 sold 28.75% of the total number of cars sold. Does anybody not see that? Because what you're looking at is relative to the total, which group sold the most cars? Okay, any questions about that? No questions? Okay. All right. Okay. So what do you want to do with this information? As I keep saying, it's easier to show the results graphically, because more people will understand it than showing a table and some kind of formulas that you came up with. They don't care about that. That's for you to come up with these tables. All right. So that is very important, especially when you're doing presentations. And okay. So when you're doing a graphic presentation of a frequency distribution, there are 3 commonly used graphic forms: the histogram, frequency polygons, and cumulative frequency distributions. Okay. Now, does anybody, and there's no correct or incorrect answer, but if you were presented with this report, which one is the easiest for you to understand? Okay, we have 2 people for histogram. How do I make that a little poll? Bar graph. Here, I'm going to So I put out a poll, if everybody can answer that. And I like those people that are not responding to respond to something. Okay, 6 more people. If you can please respond to the poll. All right, are those 6 people here with us? Going once, twice. Okay, I guess they're sleeping. Oh, all right, so somebody switched. So 17 people said the histogram. One person said the frequency polygon, and no people said the cumulative frequency distributions. So I don't know who the person is that said frequency polygon. Can that person explain why they think the frequency polygon is the easiest one to understand? And who was that? Anybody want to take responsibility for saying frequency polygon? No one. Okay. Pui Ling, can you tell everybody, or can you write down why you think it's easier to understand the frequency polygon rather than the histogram? So Pui Ling, can you explain why it's easier to understand the frequency polygon? No. Okay, can someone who said histogram? Oh, because it's only one line to show everything. Okay, that's one way to look at it. And if it's easier for you to understand a line graph, and remember, these are cumulative frequencies, so it's going from the lowest to the highest, or it's going from the low to the higher to get the total. So can one person explain why the histogram is easier to understand? Anybody? 18 of you said. John quickly seen it. What does that mean, Ocean? The picture shows height. Yeah. Okay, is it because when you look at the histogram,
when you see it, you can visually see the height difference like right away. You don't need to read numbers or anything really.
Yeah, exactly. You know which one has the greater frequencies. You
Right.
know which one has the least frequency. And when people are processing information, as I mentioned that saying about a picture's worth 1,000 words, they can process that pretty quickly. When you're looking at a line, you have to start thinking. So I guess you'd rather not think, but your brain is processing a lot faster. And so, like, if you're looking at a histogram, the group between 18 and 21 is the highest. You know it, and the group between 33 and 36 is the lowest. And you already know that immediately. And then you, as the person, you say you're the audience, and somebody's presenting the report, you can see that immediately. And then you can think of questions. Okay, why do you think that the cars sold between $33,000 and $36,000 are not selling? And then you can get into that information. Whereas if you have a line graph, you as a presenter have to spend more time explaining the graph to the people in the audience. You don't want to do that. You want to get to what is the point of this graph? Okay, so is that clear that obviously when you're doing, and as somebody pointed out, you never really see a cumulative frequency distribution. Very rarely do you ever see a frequency polygon. But, you know, I'll just say safely, between 95 and 99%, you're going to see a histogram because you want to communicate the information as quickly and as clearly as possible. And I believe everybody in the class sort of agrees, except a few exceptions, that the histogram is going to produce the more legible graphic representation of your data, which is what you want. Okay. So the histogram, it's a graph in which the classes are marked on the horizontal axis and the class frequencies on the vertical axis. The class frequencies are represented by the heights of the bars, and the bars are drawn adjacent to each other because they're a part of one sample. Okay, they're not separate samples. Sorry, I'm trying to see if there's any kind of video here. And there is. Sorry while this takes time. Okay.
Hi, well, in this tutorial, what I want to do is show you how we draw histograms. And what I've got here is a group frequency table. It records the distance thrown by a number of people throwing a ball.
I'm just going to ask a quick question. Is there anybody in the class that has not created a histogram in Excel? Has everybody done this? Because I'm not sure, how much Excel people have done in their previous classes. Yeah. Okay. Okay. For those that didn't answer, I'll continue with the video.
We've got what we call here the classes. And it's very important that we understand what the classes represent. I mean, for instance, take this class here, 10 to 14. You'll notice that there's gaps, and we're meant to be dealing with continuous data here. And if it's measured to the nearest meter, it means that that distance d has to be greater than or equal to the lower bound, but less than the upper bound. Now, what is the lowest bound for this? Well, because we're measuring to the nearest meter, the lower bound must be 9.5 meters. We'll just put 9.5 there. And the upper bound, we're going from 14 to 15. If you're measuring to the nearest meter, it must be just less than 14.5 meters. And that means that the class width isn't from 10 to 14, just 4 units. It's actually 9.5 to 14.5. So the class width, we'll just call it CW, is going to be 5 units, the difference between those two values. So what's the class width for this one here that says 0 to 9? Well, you've got to be very careful with this one because you can't throw anything less than 0 meters. Unless you threw it behind you, I suppose, but let's excuse that. What we've got here is that D must be greater than or equal to 0. But then from 9 to 10, being to the nearest meter, you've got to be less than 9.5 meters. So the class width for something like this, CW.
So does everybody understand why it's at 0.5? No. Okay, Olga. Why do you think it's separated by 0.5? Any idea? No. Okay. So in this example, it's distance thrown to the nearest. So you say you're throwing a ball and they're measuring how far you can throw the ball, or how many times you've thrown the ball between 0 and 9 meters. Okay. So you cannot have, well, somebody threw it at 9.5 meters. You don't know that because the measurements are whole numbers, correct? So in order to measure it properly, because you're using whole numbers and your frequencies are whole numbers, you can't have a frequency of, well, they threw it 18.5 times. Nobody can throw it 18.5 times. And because classes are whole numbers, you cannot have a decimal for the nearest meter, because when it says nearest meter, you're rounding it off. So therefore, what you're doing is you take half the interval. So if it goes between 0 and 9.5, or less than equal to 9.5, you round down. If it's 9.5 and above, you round up. So you remember about rounding numbers, okay? So if something is below 5, you round down. If something is greater than 5, you round up. Does that make sense? Okay, that's exactly what it is, because remember, you got to go back to what we're doing. We're talking about frequencies, and frequencies are not measured in, decimals or, fractions. They're whole numbers. And so think about rounding when if you get a question that, you have to decide on what the class intervals are. A class interval is not, 0 to 3.25. Okay, it's like 0 to 3, and then whatever. So you're rounding down and you're rounding up. So I just want everybody to be clear about that.
Will be 9.5 units. Now, why am I doing these calculations? Well, when it comes to drawing a histogram.
Okay, and remember what he's doing is he's figuring out the class width. And the class width can be up to 9.5, even though you don't measure the frequency of 9.5, because you're rounding down or you're rounding up.
We have to calculate a particular value. It's called the frequency density. It's the frequency divided by the class width. And we've got the frequencies down here, and I've shown you the class width on a couple of these. So to do this, we need to construct another column called the frequency density column. So in order to put this first value in here for the frequency density, we've got to do 18 divided by the class width from 0 to 9.5, as we did down here, which is 9.5. So if you do 18 divided by 9.5, the value you get back is 1.89, and so on. When it comes to working out the frequency density for the class 10 to 14, we've got to do 14 divided by the class width, which we know is 5 units, going from 9.5 to 14.5. And if you do 14 divided by 5, you get 2.8. Now you need to work out the other values, okay? And you might like to pause the video and give it a go.
Well, we'll let him figure it
Okay,
out.
well, these are the results, and hopefully you're able to get them right. What we've got here is we would have 16 divided by 5, because this is going from 14.5 to 19.5. This one would be 15 divided by a class width of 5. 17 divided by a class width of 10. And what about this last one? The class width goes from 34.5 to 50.5. That's a width of 16 units. So 10 divided by 16 gives 0.625. Now that we've got our frequency density values worked out, what we need to do is plot the histogram. And so we take a bit of graph paper, put some axes on, and we've got on the vertical axis frequency density, and you can see it goes up to 3.2. So my scale here goes up to 3.5. So don't forget to rule your vertical axis, the frequency density. Now on the horizontal axis here, I've got the distance measured in meters. And again, don't forget to label your scales. And I've got 10, 20, 30, 40, 50, as you can see. Now to plot these, we first of all take our first interval, which goes from 0 to 9.5. So you've got to go 9.5, and so 9.5 is just slightly to the left of the 10 here. And then you've got to go up here to your frequency density, which was 1.89, which is going to be, say, well, let's just say it's about 1.9. So you're going to then draw a bar across there. And for the next one, we're going from 9.5 to 14.5. And it's at a height of 2.8 units. Well, you could try and draw this on a bit of graph paper, but what you should get when you're finished would look something like this. So you can get these bars here having different widths, but you must make sure that they join to one another because you're dealing with continuous data. And another point that's well worth noting on these is that if you were to rearrange this equation for frequency, multiply both sides, in other words, by the class width, can you see frequency would be frequency density times class width. So if we had, say, this bar here, the first bar, frequency density, this measurement, times the class width gives you the frequency. And when you multiply this side by this side, that's the area. So what I'm saying is that the area of any bar, let's just shade this one in here for instance, that area is the frequency. Because what we're doing is frequency density times the class width. Okay, well I hope that's given you an introduction anyway to histograms and get you started. In later tutorials, what I'll do is I'll run through some kind of common questions that you can get on this.
Okay, I'm going to stop there. So everybody clear about that? That's basically how to find the width and the height of a histogram. But before, sorry, but now because you do have software that will create the graphs for you, you don't have to worry about that. And in this class, you're not going to do any graphs by hand. But it's important to know what the frequency density is and to find out what the width of your bars are going to be. So you know what it is if you see it. But as I said, there's software now that's going to create it for you. Any questions about that? No, everybody understand? Wellington, you understand? Or that's a no to the questions? Okay, okay. No questions. All right. John, you talking for everybody? Okay. Okay, why the widths are different? If you look at the screen, that is based on the frequency. Okay, so if you see the first one goes, so the first one goes from 0 to 9.5, correct? The next one goes from 10 to 14. So the width is not the same as the first frequency group. You see that, Huiling? Okay, that's how you get the width of the bars. Based on this, these are your class intervals, okay? And that's how he gets the different width. The class range. Everyone, what's the question mark about? Ocean?
Like I'm saying the width is the class range, right?
It's, yeah, that particular range, right? From its like lowest value
Of
to
the
its highest
class.
value,
Yeah.
right? And that's, okay, it is to 14.5. It is to 14.5 because he showed it here. It's rounding it. Okay. When you figure out these widths between these bars, that's based on the class width of each of these classes. Okay. As I said, you don't really have to think about that. Well,
You could just highlight all your numbers and then put graph.
yeah. Well, you don't have to do it because whatever software you're doing, it's going to do it for you, right?
Right.
You, you know, the advantage of having software programs is you don't have to spend, you know, whatever, I don't want to say 10 hours, but you can imagine if you have a lot of data and you're doing a bar chart, you don't want to spend 90% of your time creating a bar chart. You know, before software programs, that's what people had to do, and they had to figure this out.
I
So,
remember using my scientific calculator, the graphing
yeah,
calculator, when they first came out.
yeah,
Having
exactly.
to do those like point by point by point, and then it shows you
Yeah,
on a little tiny screen.
right, right.
Yeah, it took long.
You know, so the point is, you don't want to be bothered with that anymore. The important thing is analyzing the data and interpreting what it means. That's way more important. That's why, um, you know, people was, you know, like if somebody was doing their thesis and they were like running a bunch of analyses, it would take them months because they'd have to draw all these charts. And we're not talking, these are not complicated charts. These are frequency charts. You can hear me now?
Yes, you're there now.
Okay, sorry, I don't know, for some reason the microphone went off. Okay. So a frequency polygon also shows the shape of a distribution and is similar to a histogram. If you look at the graph, you can sort of see, if we had the histogram side by side, you see this point, that's the highest, and there's the differences, there's the width, there's the class interval. So if you can picture a bar chart, a bar going up to there, and it's the same as going across here, but it's a line, okay? And it consists of line segments connecting the points by the intersections of the class midpoints and the class frequencies. So if we look at the little chart up here, there's the selling price classes. The midpoint between 50 up to 18 is 16.5. That's the regular frequency for this class. And that these numbers are the ones being plotted on here. And as you know, when I asked you that little polling question, yeah, you can sort of see what the highest one is, you can see what the lowest one is, but you really don't know what these numbers are. You know, well, you do know what the numbers are, but it's a lot easier to understand the bar chart or the histogram than this. Okay? You can see where the frequency is higher, you can see where the frequency is lower. But visually, and this is how our brain processes this information, the other one is a lot easier to understand. Okay? So, what I'm going to do is show you the video on the frequency polygon.
Say you were given a special project to analyze the data from last week's track meet, and you were really excited to share the findings with your class. However, when you start looking through the data, you are overwhelmed by the numbers and wonder how you can make it more visually appealing. Then you remember that your math teacher just taught you about frequency polygons, so you decide that is a great way to organize the track meet data. A frequency polygon is a type of line graph that shows the frequency of a mutually exclusive event occurring. Seeing the data in this format helps us visualize and understand it better. All frequency polygons must have a title, x-axis, y-axis, and data points with a line connecting them. The x-axis shows each of the mutually exclusive results from the data. The y-axis is a scale that shows the frequency of that result in the data. The data points are dots on the graph that align each mutually exclusive result with the frequency of its occurrence. Then a line is drawn.
Okay, that's certainly enough of that. Okay. So is anybody not clear about a frequency polygon? And as I said, it's not used very often. Okay. Whoops, sorry. Okay, so histogram versus a frequency polygon. Yes, both of them provide a quick picture of the main characteristics of the data, the highs, lows, points of concentration, etc. The histogram has the advantage of depicting each class as a rectangle, with the height of the rectangle bar representing the number in each class. The frequency polygon has an advantage over the histogram. It allows us to compare directly two or more frequency distributions. Yeah, that's true, because if you look on the left side, the left-hand graph, you can put two frequency polygons on the same graph. Actually, if they have the same measurements or you observe the same measurements. But other than that, the one on the right is still easier to understand. Okay? I'm not going to stop anybody from with the case study. If they want to use a frequency polygon, that's fine. That's up to you. Okay? But the histogram is a lot easier. Okay. So the cumulative frequency distribution, which nobody said was visually understandable, that you had to look at different things here, and obviously you do. Again, I'm going to show you the video. It's not something that is expected for you to do, unless, of course, that's something you want to do. So basically, it's just so that you know what a cumulative frequency distribution is. All right. And sorry, I've got to do the share thing here. Oh. Sorry. Okay, that didn't do anything.
For this video, I want to show you how.
Okay.
To make a cumulative relative frequency chart. If you've never heard of one of these charts before, let's see exactly what we're making. In a cumulative relative frequency chart, we're interested in knowing the total relative frequency up to a given data value. This means we'll often need to look at the relative frequency and add up values less than or equal to some given value. It's actually not as hard as it seems, so let's grab some data and see what this looks like. So here I have some data that records the number of food cans collected from a given food drive. On day 1, they collected 1 can, day 2, another 1 can, day 3, they collected 2 cans that day, so on and so forth. So what I want to do with this is basically write down my data values and do the relative frequency for each of the data values. That way I can come up with the cumulative relative frequency. So let's see what we got. Let's do the number of cans. We'll do their relative frequency. And here's where we will put the cumulative relative frequency. So 0 cans, 1 cans, 2 cans, 3 cans, and 4 cans. Right, for the relative frequency, we want to see how often these appear divided by the total number of data points, which is 15. So starting off with 0, I see it appears on my list once, divided by 15, a relative frequency of 0.07. I see 1 appears 1, 2, 3, 4, 5 times, divided by 15, I get 0.33. Let's see, 1, 2, 3, 2s, divide that by 15. 1, 2, 3, 4 threes. And it looks like just a couple of 4s. So 2 divided by 50. If you need help with this, check out my other video on building a relative frequency. All right, so now that we have all of our relative frequencies, the cumulative frequency will keep track of the total relative frequency up to this point, all right? So starting with 0, my total right now is just 0.07. For my next data value, I want the total relative frequency up to this point. So this would be 0.33 plus 0.07. So now my total is up to 0.4. For here, I want the total of...
So I just want to stop there because basically this is what the cumulative relative frequency is. When we have this, okay, we have, so for the first row we have 0.07. That's the relative frequency out of the total. So the cumulative relative frequency is 0.07 because it's the first measurement. Basically, the second one, you have 0.33, and then what you do is the cumulative relative frequency is you add the 0.33 to the 0.07, and that's how you get the 0.40. So who can tell me what the next cumulative relative frequency would be? Okay, Brenda, why is it 0.53?
The 0.33 plus 0.20.
No. Okay, so what you're doing is the correct answer is 0.6. Here you added 0.07 to 0.33, correct? Oh, you got it? So the next one would be 0.40 plus 0.20, which is 0.6. All right, it's as simple as that. There's no complications here. All right, so I'm just gonna continue.
0.2 plus 0.33 plus 0.07. As you go along adding different values to your cumulative relative frequency, you can see that you're just adding everything up before that point.
And so when you add them all up, what's your final answer? 1, exactly, Wellington, exactly. So this should always add up to 1, because basically all you're doing is adding these 3. And the cumulative frequency, that's why this is not a very popular graph to show, because people don't really care about this group plus this group and then plus this, like, so what? Okay? Unless there was some kind of relationship, say, between the 5 of these classes, then it might make sense that, say, oh, you know what? Okay, so say we do this and we have the 60%. That means 60% is part of the first 3 groups. But so what? That's why I said they have to have some kind of an importance into the data that you're looking at. And that's where you would actually use the cumulative relative frequency. Any questions about that? Okay, I don't hear any questions. All right. So it's not something that you're going to do every day, and it's not something you're going to see every day. Okay. Your can, or in this case, the number of cans, your classification categories have some kind of relationship to each other. All right. I mean, you could say, well, 60% of the cans collected were less than 2 each time. Okay. Does that mean something? I don't know. Unless it's explained, then really the presentation of this doesn't have any meaning for your audience.
If you want to make this process go a little bit faster, when you're filling in this last column, you can just add up the previous value since it has already added up the ones before that. All right, so adding up everything before it looks like we get 1. And if you do this process correctly, this last value should always equal 1 because the total relative frequency should equal 1. All right, so just like that, now we have the cumulative relative frequency. So I can see that each of these represents a total of the things before it. If you'd like to see some more math videos, please visit mysecretmathtutor.com.
Okay. Well, let's go back to the PowerPoint. All right, here's another one. Oh, that's the ogive. That is what's called a cumulative frequency polygon, which we just saw the video on, is a type of frequency polygon that shows cumulative frequencies, which was discussed in the video. So in other words, the cumulative percents are added on the graph from left to right. That's a quick question. Has anybody ever seen a cumulative frequency polygon? No. Has anybody ever seen one? Okay. So the chances of you ever seeing one are probably nil. Well, let's put it this way, 0.01, because we're going to talk about probability. It's going to be very low. So an ogive or cumulative frequency distribution plus cumulative frequency on the y-axis and the class boundaries on the x-axis. It's very similar to a histogram, only instead of rectangles, an ogive has a single point marking where the top right of the rectangle would be. How exciting. And it's usually easier to create this kind of graph from a frequency table. So that's probably the first and last time that you know, well, you might get it on the quiz or the test about ogives. Okay, continuing with that, here's an example. Draw an ogive graph for the following set of data. First, you make a relative frequency data table from the data. The first column has the class limits. The second column has the frequency, which is the count, and the third column has the relative frequency, the class frequency divided by the total number of items. Okay, similar to the video. So you add a fourth column and cumulate. You add up. That's what cumulation means. The frequencies in column 2. Going down from the top to the bottom, for example, the second entry is the sum of the first row and the second row, as you saw in the video. So the first one, now they're doing, in this example, it's a raw frequency. It is not the percentages, but if you add up the percentages, they should also add to 1. Okay, the cumulative frequency adds up all the frequencies, and in this case, it's 25. So the next step, oh, they put an extra step in to put in the cumulative relative frequency, which is the fifth column, and accumulate the relative frequencies from 1 to 3. If you do this step correctly, your value should always add up to 100% or 1 as the decimal. All right? So you know when you do this, it's similar to a pie chart, except what you're doing is you're adding one frequency to the next frequency. And then so on until you finish all the classes and get to a total of 1. So is that somewhat clear about cumulative relative frequencies or ogives? Sure? Okay. You're the only one, John? Okay. And here, continuing, you draw an Y graph with the percent cumulative frequency on the y-axis from 0 to 100%, or as a decimal 0 to 1. You mark the x-axis with the class boundaries, and you plot your points. each point should be plotted in the upper limit of the class boundary. So for example, if your first class boundary is 0 to 10, the point should be plotted at 10. And the next one was at, your cumulative, you're adding it up. Remember, these are frequencies. You're adding it up, so it eventually adds up to 100 or 1. You connect the dots with straight lines. The ogive is one continuous line made up of several smaller lines that connect pairs of dots moving from left to right. At the bottom, this is your graph. Anybody want to be talking or what you're talking about? I can hear somebody.
Story. No, sorry, baby.
Anything, is that relevant to the class or not? What you were talking about, whoever that was? No? Okay, if you're going to talk, go offline because everybody can hear what you're saying and it can be distracting. All right. A stem and leaf display. Has anybody, okay, I'm not sure whether people have seen this, but has anybody seen a stem leaf display? Oh, everybody has seen this. Oh, Wellington, you haven't seen it. Olga, no. Okay. I'm not, I'm just curious, was this covered in your original math course or was it covered in another course like economics? Like where did you come across stem leaf displays? Econ, okay, not math. High school, okay. All right. High school stats, okay. That's I just find that interesting. It's also a visual representation that is not really popular. Well, at least not from my experience, it's not very popular. So it's possible that it's more popular in economics. Sorry, and my microphone went out. I clicked the wrong page and it didn't register what I said. Okay. All right.
What we have is we have the median age of all the residents in each county of Maryland. In addition, we also have the median age of all the residents of Baltimore City. The first.
Okay, so what they're doing here is, and everybody remember what the median is? It's the middle. It's the absolute middle of your data set. It's not the mean, it's the middle. It could be the mean, but let's just say it's not the mean because it doesn't usually happen at the same time. For counties in Maryland, and you have the median age, and this is from the 2000 US Census, and they're going to create a stem and leaf plot to display the data distribution for the median age for Maryland counties and Baltimore City.
Thing we need to do when we're given any data set is to look at the data graphically. One of the tools that we can use to look at a data set graphically is the stem and leaf plot. Let's construct the stem and leaf plot for this data set. Once we have the plot, we will use that graphical representation to describe the data distribution shape, its center, its spread, and whether there are any outliers in the data set. When constructing a stem and leaf plot, the first thing you must decide is what part of each data value will be represented by the stem and what part of the data value will be the leaf. In our particular data set, we are going to let the integer part be the stem and the decimal part be our leaf. So let's start by writing all our stems for our stem and leaf plot. Our stems go from 33 years up to 43 years. Once we have our stems, draw the vertical line that will separate the stems from the leaves in our plot.
Okay, so just so how she got the stem, everybody understands she's taking the rounded median age. So the lowest one is 33 and the highest one is 43. Okay, that's the stem. The leaves are going to be the decimals. All right.
Now we're ready to graph each of our data values. Our first data value is 33.3. We come down, we have a stem of 33. We want the leaf to be 3. We have a data value of 33.3 years. Our next data value is 34.2 years. Our stem will be 34, our leaf will be 2. We also have a 34.6 median age, so we put the 6 right here. How many data values will we have that start with the stem of 35? There will be 1, 2, 3, 4, 5, 6 data values that begin with the stem of 35. 35.0, 35.5, 35.5, 35.6, 35.8, and 35.9. We have a 36.0, 36.2, 36.5, 36.8, and a 36.9. We have a 37.0, 37.4, and a 37.7. 38.3, 38.8, 39.1, 40.7, 41.3. We do not have any median ages that begin with the stem of 42, so we just leave the leaf part that has a stem of 42. We just leave that blank. Then we have a 43.0 and a 43.3. All of our data values have been plotted. Now we need to add the 2 things that must be included with every stem and leaf plot. You need a title describing what is being graphed in your stem and leaf plot. And you also need a key so that to let the reader know what the stem represents and what the leaf represents in the stem and leaf plot. So let's do that now. Our title is Median Age for Maryland Counties and Baltimore City. And our key is 39 line 1. That represents 39.1 years. Do not forget to include years. So now the reader knows that the numbers to the left of the vertical bar represent whole number of years, and then the digit to the right of the vertical line represents the decimal number of years. Now that the stem and leaf plot is complete.
Okay, I have a question. In what kind of circumstance or condition would it be advisable to use a stem and leaf plot? Can anybody think of it, or what were the examples that you can remember from econ or from previous math classes? Well, you can see this one where it's 35, where the median age is 35, you have the most frequencies there, right? So you know that people who are in the 35 years old range have the highest frequency, correct? And if you look at this in a certain perspective, it sort of looks like if you join the highest number for each stem, it could look like a normal graph. Can people see that? Yep. Okay. Like, is that helpful? In a way, you can look at it and say, you know, is the graph flat? Is it skewed? Do people understand the concept of skewed? There can be more frequencies on the left side or more frequencies on the right side, which would not end up giving you a normally distributed graph. So this one looks like, you know, it's skewed from the left side from like 33 to 38, whereas from 39 to 43, you only have one or two values. Okay? You can certainly see that from a frequency histogram as well. All right, sorry, I'll just continue.
You want to use that graphical representation to describe the data distribution shape, its center, its spread, and whether there are outliers or not. What is the shape of the data distribution? We can clearly see from our stem and leaf plot that the data distribution for the median age of the counties in Maryland is right skewed. If you watched or you go back and watch.
Does everybody understand that the shape is right skewed? You see there's more value, there's more frequencies on this side. Okay?
The video that describes how to do a dot plot as your graphical representation of data. You will see that we use the exact same data set in that video and we constructed the dot plot. From the dot plot, it was much more difficult to see the shape of the data distribution as compared to the stem and leaf plot. Where is the center of the data distribution? I would say the center is somewhere in this region. So I'm going to say that it's probably between 36 and 37 years. After doing the graphical representation, you will go on and do numerical summaries for your data distribution, and you will get a numerical summary for the center of the distribution. But just looking at the data distribution, I would say it's somewhere in this region. What's the spread? Looking at data distribution, we can use the maximum value, 43.3 years, and subtract the minimum value, in other words, the range of the data, as our measure of spread. We see that our spread of the data is about 10 years. Are there any outliers in the data set? I would classify the top two ages as outliers, and I would probably even include the 41.3 years. This is subjective, looking at a data distribution, looking at the data graphically. Different people will have differing opinions as to what is an outlier. Again, after looking at the graphical representation, a more objective look at the data, using the actual data use and numerical summaries would be done to get a firmer grip on whether 41.3 was an outlier or not. Just looking at the data, I will classify 41.3 years, 43.0 years, and 43.3 years as outliers. Again, a stem and leaf plot should only be used if the number of data values in your data set are relatively small. The reason for that is we have to plot each and every one of the data values in our stem and leaf plot. So if the data set is large, it would be rather cumbersome to create a stem and leaf plot for such a large data set unless you were using a computer program. One of the advantages of a stem and leaf plot over a histogram, however, is in a stem and leaf plot, You do not lose any of your data values. You can go back and you can reconstruct your data set from a stem and leaf plot. You cannot do this when you use a histogram. So a stem and leaf plot can be a very useful tool in describing a data distribution shape, its center, its spread, and whether it has outliers or not, if the number of data values in the data set is relatively small.
Okay. So I'm stopped for today, and there's just a little bit more about stem and leaf, and we should be actually finished chapter 2 on Tuesday. I'm not sure, but it looks like it because there's not very much left. So is there any questions about today's class? No questions? Okay. So I'm just going to remind people that as of 5 o'clock, you will have access to test 1, which is covering chapter 1, and you will have between 5 o'clock today and 5 o'clock on Monday to complete the test. And remember, you can only do it at one sitting. And are there any other questions not necessarily related to today that somebody may have? Yes, the test is on chapter 1. Any questions about, yes, Brenda? What is it that you want to ask about the assignment for chapter 2? I believe I said that it was due next week, next Friday, that you should send your homework to me electronically. So send it to my email. I can't guarantee I'll get it back. Should we write it in our words? What does that mean? What do you mean by that? Your own words, please. Yes. Yes, your own words. Please write your responses in your own words, because that's going to tell me whether you actually understand the comments. Or sorry, the questions, not the comments. Any other questions? Okay, I'm going to present this to you, and I'll talk about it in upcoming classes. You know, not to say that it's going to change, not to say that it's going to stay the same. But when I had the 2 office hours on Monday and Wednesday, so far I've only had one person come to the office hours to ask me questions. So what I was thinking was, and you know, everything is flexible. How would people be receptive to us doing some lessons on, like, say, SPSS or SAS? And remember what I mentioned, you have to you have to get it from the GBC apps anywhere. So you have to download it, or you download apps anywhere. So are people at all interested in that, in learning that software? No one is interested? Okay. Not too much. You don't want to learn too much? Okay. So Ocean, you're the only one that responded. Maybe I will send out a, not too much of that software. Okay. Yes, you can. Although I'm not sure how it works, whether you go on the cloud and then you use the software, but you have to have the apps anywhere on your machine. You don't necessarily have the SAS software or the SPSS software. Okay? Because as I mentioned in the first class, when you are going to, if you're going to apply for jobs, it's good to know about the software and have to have some experience with the software. I know this is an introductory stats class, but it's also good to be familiar with the software, because believe me, as somebody who had to do statistics by hand, having access to a computer and access to software is very helpful. Okay. So if there's no other questions, I'll end the class, and everybody have a good weekend. And if there's any questions, please send it to me. I can't guarantee I'm going to get respond to you in a quick manner, just because it's the weekend and we all have different things to do. But remember to access the test, do your homework, have a good weekend, and enjoy the sun, because it's not going to rain. Okay. Thank you, everybody.